So when you do this, you have this equation equivalent, and then find out the minima requirement. You will find out the z need to be equal to 1/3 of z0. Okay, this position is exactly at 1/3 z0. Okay, so that means you can move the actuator in the maximum distance up to 1/3 of the z0. That's the maxima of the your finger, the actuator, which can go. Okay. So you cannot go further. Go further will be pulling, but in this position there will be a separate area for the second curve here. Okay, that's the maximum distance you can go for this actuator. So still 1/3 of the gap is still not very much actually. Okay, so that's why we always say the gap closing method to operate the system. The displacement is not as much as like the lateral driven one. Lateral driven one can easily go up to like a couple micron, but for gap closing usually is less than one micron. Yeah, even though it can provide a larger force, however the displacement is sometimes quite small from this point of view. So this curve show you if we change the voltage of the electrostatic force, so what kind of interaction you will have. Another thing is that you can consider, you want to design the spring to fit into your system. If you have one kind of driving force you already want to have, and this driving force has already been set, you cannot change. So you have only one curve for the electrostatic force. So now you want to change the spring constant of the spring. Okay, try to make the situation optimized. So here it shows you 3 different curves with different slopes. Slopes means the spring constant of the spring. So you can gradually increase the spring constant from the first one and into the third one. The third one has a larger spring constant than the first one. So until some design, the spring constant of this design just encounter with the curve here at one point. Okay, so that gives the optimized design of the spring system. Okay, yeah. So that's why in the spring system, it's not just a arbitrarily draw a structure and passively find out the final spring constant and plug into your solution that can give you the final result. No, you need to consider the situation here. Okay, try to adjust your spring constant until this situation happen. Okay, and they encounter at one point. That means you have a maximum movement distance of 1/3 of z0, original gap, 1/3 of the original gap. Okay, there's a design starting from the spring constant variation. Okay. Okay, after understanding this, now we need to consider another situation we call the buckling of a long beam, because you have a very long beam, right? You fold a long beam, and also you want to make a very soft spring, so the beam becomes very, very long. So for long beam, another thing you need to consider is if we push the beam may be bulk up. When the beam bulk up, there will be situation happens. The overlap of the finger will become non-overlap. If you push the whole the center part of the actuator above the surface too much, that's a problem. So the system will fail. Okay, so the situation coming from the buckling. The buckling sometimes is not from the electrostatic force, because electrostatic force is usually very small. It's coming from the fabrication. After fabrication, remember, we always build up some stress inside the beam. Sometimes it's a compressive stress, sometimes it's tensile stress, even sometimes we have a stress gradient, uneven stress. So those things may bulk up the beam. Okay, so now we consider if we have the beam encounter compressive force. For tensile force, it won't bulk up. Okay, only for compressive force. So now we consider the beam encounter compression force. The compression force, if the compression force is large enough, the beam will start to bulk up. When the beam starts to bulk up, the situation looks like this. So you take a small portion of the beam, and to analyze the force balance and the moment balance among the beam, you can find out the equation like this. Okay, so the curvature, okay, will be equal to your bending moment. The bending moment here, okay, at this position, will be the force P times this distance, the arm, delta minus y. Okay, the arm is over here. Delta is your deflection. Okay, the total deflection. Y is the position over here. So your delta over minus y is the distance, the arm over here. And we got the 3 boundary condition. So at x equal to 0, at this position, you got the position y and the slope equal to 0 at the center position. The other one is at the end. At the end, you have a deflection y equal to delta. Okay. So these 3 boundary conditions we can plug into this equation to solve the equation. Okay. Look into this equation. This equation is different from before because when you integrate this equation, you got a 2 constant. That means a 2 constant. You need to have a 2 boundary condition to solve it. However, in this equation, not only two constants you will have. Another thing you don't know is the delta. What kind of displacement you will have here? You don't know actually. So the delta is an unknown parameter. So that's why we need 3 boundary conditions to solve this equation instead of only 2. Okay, with extra parameter delta, which need to be solved by the boundary condition here. Okay. So now we plug into the first boundary condition into this one, and find out this equation here, the first boundary condition. And we have a first boundary condition have this partially solved the equation plug into the second boundary condition, and when we plug into the second boundary condition, x equal to 1/2 L. And the y equal to delta. The delta will be cancelled from right hand side and left hand side. So now we have only this part equal to 0. Okay, so we apply into all the boundary conditions. We found out finally this equation becomes 0 because the cosine is a periodical function. So now we can find out many solutions for this equation. So n out the integral of the pi over 2, you will see the odd number of pi over 2 will become the solution. So when we take out the smallest one, this is the smallest boundary condition which can fit into the solution. For larger value, that means the buckling of the beam is not forming like one curve, like one wave. They will become several waves if a higher order solution. The buckling of the beam becomes several waves, not only one wave. Okay, now you have only one wave. This is the smallest condition. You can have a higher order condition. 听得懂吗？就是你现在错区的话只有个肚子，对不对？假设你用比较高次的那个解带进去的话，它变成 wave 好几次。好，所以你的 buckling 不见得只会 buckling 变成单一个方向，它可能是像这样的一个 wave， 也可能有好几个 wave 在里面，这是有可能的。所以那是高次的解。好，当你非常非常软的时候，是有可能变成那样子的。OK， 但是我们现在只考虑第一个解。So now we consider only the most simple one, pi over 2, this case. So we find out the important equation is the pre-critical. So the critical force you apply onto the beam to bulk up the pin will be equal to this equation. So the critical force will depend on several things. The first one is the Young's modulus. The Young's modulus means the rigidity of the beam. So if the beam is not rigid enough, okay, the small Young's modulus, so the pre-critical can be small. In small force, the beam can be bulked up easily. And also another thing is that your momentum of inertia. When you bulk up the beam may be not a symmetry in all three directions, okay, for the momentum inertia. So the beam will bending towards the weakest I value, the position of weakest I value. For example, like a ruler, you push the ruler will bend along the thinnest part, okay, that direction, not the thicker part, okay. So this depends on the momentum inertia. Another thing is regarding the length. So you have a longer length, you also will reduce the peak critical quite quickly. So make the beam become very, very weak, easy to buckle out. Okay, so so this is a peak critical. So this peak critical, remember we developed the peak critical by using this model. This model you can see we have two ends can have a free rotation, but the position is fixed, but the angle, the rotation is free. Okay, so we developed this equation based on this kind of assumption. So this is exactly the same case showing here. So we fix two positions, but we allow them to rotate. So like we put the two rollers at the end. So when we push down, the beam starts to buckle, and also the position here is fixed, but it can rotate. So this gives you the equation of this. We call it 1. If you calculate the force, finally we normalize them. So normalization after normalization is equal to 1. And this situation is equal to the second situation. But they look very different. Why they are the same? Okay, when you look into this kind of situation, so when you have this kind of bending, you can cut this beam into two parts, the top part and the bottom part. You cut at the center. You have a top part and bottom part. And the top part and the bottom part, you can consider the center part. At the center one, you got the, if you have a line over here, join the line over here, you have the beam always vertical to the line I just draw. Okay, so it looks like a cantilever beam over here. You have two cantilever beam, one on the top, the other one on the bottom. They connect to each other, similar to we just mentioned before. You have two cantilever beams connect to each other at the center. You push, they will deform. So this one similar to this one because when you cut at the center, you connect this one and the bottom one. You take the top one, okay? You connect to the bottom one and try to rotate in 90 degree, 180 degree. So the final curve will be exactly the same as this one. Do you understand? No? Okay. So you cut it to half, okay? And take this one at the bottom. Originally it looked like this, right? This one, put it here, and then you flip it over. So you got it like this. So the curve here now was similar to this one, right? You take the top one, put it here, and flip it over. Now connect here. So you got the final curve exactly the same as this one. So they are the same case. So that's why the equation is the same. It's also 1. Okay? Another case is this one. This one is only 1/2 because the length here is the length here is twice the length here. So you don't need that much force. You can bend it over. Okay? Because you cut to half. So the half of this part is similar to this part because you can fix this end and then consider the deflection on the other side. It's exactly like this one. But the length is twice. So if you put the twice the length into this equation, the P-critical becomes 1/4. It becomes easier to buckling. Okay? So it's 1/4. The third one is a little bit difficult. You need to do some calculation. The first one, you can cut this piece into 4 pieces. Okay, 1, 2, 3, 4. Each one is like one cantilever beam. Okay, but the length become 1/4, become shorter. Okay. Okay. Oh, sorry. This one. Okay. This one is similar to this one, right? This one is similar to this one, but the length is a half length. So you plug into L equal to half length, you got the P critical become 4 times. Okay. So currently we have the beam similar to this one. So this one is similar to the P critical. But if you force the the position, for this one we have a crab leg. Remember, so the deformation will allow the movement or the position here to the side. However, if you don't allow the movement on the sides, you fix the position of this end, so it will become 4 times larger. I mean the buckling. Okay. Situation. Okay. Now we will use this one for calculation for our crab leg. Actually, for the individual cantilever, it looks more like this. Okay. But you need to remember, in your future design, you may encounter different types of the beam design. Okay. Okay. So we still have some other things. So maybe we stop here to take a break, a little break, and then come over later. Okay. Thank you.